Hi, Christine. So I think we're going to start right now. It's about 3 minutes after.
Sure.
Great. Okay. Thank you, everyone. Welcome to the GISS lunch seminar from today. Thanks for coming a bit early and for accommodating. I hope that other people took kind of mental note that this is happening about an hour earlier than we normally schedule these seminars. I'm really happy to have today Dr. Christine McKenna presenting from the University of Leeds, where she's a postdoctoral fellow working with Amanda Maycock. Christine received her PhD from Cambridge, where she was supervised by Peter Haynes and Emily Schockberg. And Christine's kind of overall interests are in looking at future projections of the large-scale atmospheric circulation, primarily with a focus on constraining uncertainty in these projections. So I came across kind of a recent manuscript that Christine had prepared looking at future projections in the North Atlantic Oscillation, the relative contributions of kind of model uncertainty and internal variability. And I found this work to be really interesting, especially as it utilizes large kind of multi-model ensemble projections. So with that, Christine, please feel free to share your screen. And we're recording this presentation for people who can't see it. We're going to be utilizing the chat feature as we have in the past. So if you have a question or comment, just indicate that in the chat and I'll ask you either to unmute yourself or I can read the question. And without further ado, please feel free to start, Christine. Thanks.
Thanks very much, Clara. It's a pleasure to be here today and to be invited to speak to GISS. So today, as Clara said, I'm going to be talking about a recent study that I did that was published in GRL, and this was with Amanda Maycock, and it was looking at the sources of uncertainty in multi-model large ensemble projections of the winter North Atlantic Oscillation. And so this work is part of a larger European Union funded project called Constrain. It's got like 13 different partners across Europe, and the overall aim of the project is to constrain uncertainty in multi-decadal projections. So, oh sorry, my slides aren't moving forward. Oh. Don't know why they're not.
So I can see your laser, so at least that's working.
Yeah, my slides aren't moving forward. That's strange. Maybe if I go out of presenter view and back. Apologies, the glitch already. I'm going to try again. Still not working.
So obviously, if you advance with the arrows, obviously that doesn't work.
Yeah, it's not working. I don't know why. Maybe if I share my screen instead. No, it's just not working.
Do you have kind of a PDF? Is this maybe that might be easier to navigate?
Yeah. Just opening a PDF. Not sure how to put it into full screen.
Yeah, you should, exactly.
There, can you see that? It's moving now, isn't it?
Yep, that's fine. That looks great.
Yeah, okay. Sorry for that, everyone. So yeah, as I was saying, so just first of all, just a broad outline. So I'll first talk about the kind of background and motivation as to why we looked at this subject and give you kind of quick explanation of what multi-model large ensembles are. I'll then go on to talk about the aim of the study and the four research questions that we aim to address in the work. Then go through the methods and the results with respect to each of those research questions. And then I'll round up with some conclusions and open questions and idea for future work. So first of all, a bit of background and motivation to the study. So for like thermodynamic variables like global temperature, I'm sure we're all aware that anthropogenic climate change is pretty robust, so it's discernible from internal variability. But when it comes to the dynamical aspects of climate change, such as changes in the atmospheric circulation, there's far less confidence. And this is a problem because projections of the circulation are particularly important for understanding the more regional impacts of climate change. It's all very well knowing what the changes of global temperature are, but in terms of impacts on humans on the ground, like it's important to know those regional changes. And so this little schematic, it shows the regional impacts associated with different phases of the North Atlantic Oscillation. So the mode of circulation that I'm going to be talking about mostly in this talk. And so I'm sure you're all familiar with this already, but just in case there's anyone who's not, so in its negative phase, we have like a weakened low in the northern latitudes of the North Atlantic sector, a strengthened high in the southerly regions, and this is associated with a southward shift of the eddy-driven jet, and in winter that brings colder weather and drier weather over northern parts, and wetter, warmer weather over southern parts. And then in the positive mode, it's kind of the opposite. So these are the particular impacts of the North Atlantic Oscillation, which makes it an interesting, mode to understand how it's going to change in the future. So in the North Atlantic in particular, there is substantial spread in projections of the North Atlantic circulation across the CMIT-5 and the CMIT-6 models. This has been shown in various studies, which I've listed here. This figure is taken from a study by Ted Shepard in 2014, and it shows the ensemble mean response of the lower tropospheric wind in the North Atlantic sector in winter to climate change over the 21st century under the high-end emissions scenario, RCP 8.5. And you can see there's really quite different changes in these winds. So, for example, if we look at EC Earth, you kind of see a more southerly shift of the jet stream over continental Europe. And then if you look at this model here, you see more of a northerly shift. So we're seeing quite different impacts. So what are the sources of this uncertainty? Well, for a given future forcing scenario, there are two types of uncertainty that can arise. So firstly, we have structural model differences, and by that I mean differences in the forced response to the same external forcing across models that arise due to differences in the model physics, the model's numerics, which cause it to respond differently. And this type of uncertainty is potentially reducible. So if we can understand better the processes that cause those differences between the models, then we can maybe hope to reduce that uncertainty. The second type of uncertainty is from internal climate variability, or IV. So this is the natural oscillations we get in the atmosphere due to the nonlinear interactions between the atmosphere and the ocean. So if we set one model off with exactly the same external forcing and lots of different initial conditions for each ensemble member, we'll see those ensemble members diverge pretty quickly over time, and that causes a range of possible futures to occur. And this type of uncertainty is irreducible, so we can't hope to reduce that uncertainty, it's just integral. So for the CMIT-5 and CMIT-6 archives, the models that are available in those archives typically only have a small number of ensemble members available. And this is a problem because it makes it very difficult to distinguish these above sources of uncertainty. And so this is an issue because to be able to use the projections, we would ideally know where that uncertainty is coming from, because the type of uncertainty that dominates will determine how we use those projections. So if IV dominates, then we need to take a kind of probabilistic risk-based approach. if the structural model differences are dominating, then really our focus should maybe be on trying to reduce that uncertainty. So in this work, we used a recently available data set called the Multi-Model Large Ensemble Archive, or MMLEA for short. And the beauty of this data set is it allows us to quantify these uncertainties I just mentioned. And so a large ensemble is essentially, it's just an ensemble of projections from a model with the same external forcing and different initial conditions. So if we look at the schematic here, look at this model here, the different coloured thin lines show each of the ensemble members started from different initial conditions. And so we can quantify the spread due to IV from the spread in these ensemble members. In the multi-model large ensemble archive, we have multiple models, and so we can calculate the ensemble mean. So that is the thick line across all the ensemble members for each of the models. And then that allows us to calculate the spread in the forced response due to structural model differences. So the overall aim of this study really was to better understand the projections of the North Atlantic circulation and their uncertainty across models using this large ensemble archive. Our particular focus is on the North Atlantic Oscillation, or the NAO, which is the first mode of variability in the North Atlantic sector, and that's really why we focused on that mode. So to help address this overall aim, we asked 4 different questions on different subjects. So the first question is the key one. So what are the relative contributions of internal variability and model structural uncertainty to the spread in NAO projections? Secondly, we wanted to ask to what extent is the spread in the North Atlantic circulation projections explained by the NAO? So how much does that spread project onto the NAO spatial structure? Thirdly, we then asked when do the forced NAO response and model differences in the forced NAO response emerge from internal variability in the 21st century? And then finally, we quantify the minimum ensemble size required to separate both the forced NAO response and model differences in this response from internal variability. Throughout the talk, I'll discuss the implications of these various questions and their relevance. So the methods that I use to address these questions mainly consisted of using lots of different model simulations. So I have the MMLEA models. So these are listed here in the table. There's various ensembles available, covering different periods, but all covering the common period 1950 to 2100. They've all got different ensemble sizes. So the largest one is MPI at 100 members, and then the smallest is EC Earth at 16 members. And these are I use the historical and the RCP 8.5 simulations. I also make use of the CMIP 5 and the CMIP 6 simulations. So in particular, the historical and the RCP 8.5 simulations. I use the SAP 585 simulations for CMIP 6, which is the closest scenario to the RCP 8.5 scenario in CMIP 5. I also make use of the pre-industrial control runs to help quantify internal variability for the CMIP models, because the historical and RCP, SSP simulations don't have enough ensemble members to quantify that. I also do a bit of evaluation of the models against observations using 3 different data sets. So we have the 20th century reanalysis, ERA 20C, and then an observational large ensemble. This is essentially an 1,000-member ensemble, which contains the synthetic historical trajectories generated by a statistical model using observed climate statistics. And then the main variables that I look at are the winter, so DGF, mean sea level pressure, and the NAO index. And the index that I'm using here is from Stevenson et al. 2006. And it's the difference in area average pressure between a northern and a southern box. So moving on to my results, I'm going to firstly walk through a kind of overview of the projections, and then I'll delve into each of those research questions that I outlined at the start. So this slide shows projections of the NEO in winter for the late 21st century, so specifically the 20-year period 2080 to 2099, relative to a baseline of 1995 to 2014. I'll just walk you through all of the stuff on the figure. It's very detailed, so it's a lot to take in. So the CMIP6 models are shown by each of the dark blue bars. The light blue bars show the CMIP5 models. The darker shaded bars show the multi-model mean. And then these hatched bars show modeled anomalies, which are larger than 2 standard deviations of internal variability. And this is based on the pre-industrial control simulations. So what we can see from this is that the overall multi-model mean anomaly is positive. But this is relatively small compared to the really large ensemble spread across the CMIP models. While we have some model anomalies which are very large and positive and greater than internal variability, most of the model responses are not distinguishable from IV, and we have some small negative responses. Just to give an idea of what this spread means, like an idea of what the magnitude is, I've plotted these whiskers here in grey, and these are basically trying to show what the magnitude of low frequency variability in the NEO is in the real world. So to get these, I just take the observational record and calculate the standard deviation of random differences in 20-year means. And what we can see is that this spread is about equivalent to the magnitude of this low frequency internal variability. So, you know, it's notable. It's not just a small spread that's insignificant. Now, so because we've only got a few ensemble members available for each of these bars, these are indicated on the top of the bars in the small numbers, it's impossible to say how much the spread is coming from model differences or internal variability. And so this is where the multi-model large ensemble comes in. So each of the circles here are showing the ensemble mean or the forced response, and then these whiskers show the 95% range of the anomalies across the ensemble members. And what we can see is that indeed there are very large structural model differences of about 5 hectopascals. And equally, if you look at say the yellow model, so that's MPI, you can see that there's also a very large spread due to internal variability, about 5 hectopascals as well, so kind of equivalent. I'm now going to do some more detailed decomposition of these uncertainties. So this is using a method published by Nicola Mayer and others in 2021. And this is to address this question: what are the relative contributions of IV and model structural uncertainty to spread in the NEO projections? So the calculation is quite nice and simple. I'll just walk you through it briefly. So to calculate the uncertainty from internal variability, what we do is, so for each of these models, we calculate the intermember, so a cross ensemble standard deviation in the NEO index change, and then we average that across all the models. So that gives us this UIV. And then to get the uncertainty for model differences in the forced response, we take the ensemble means that in the circles, calculate the intermodal standard deviation in those ensemble means, and then we subtract a small offset which quantifies the uncertainty in the ensemble means due to internal variability. That gives us UMD. And the upshot of this is that we find that about a third of the spread in the model projections is from internal variability, and about 2/3 is from model differences. And so the implication of that is that for late 21st century projections of the NEO, a dominant proportion of the spread is caused by reducible uncertainties due to structural model differences. And so if we can better understand the processes that are contributing to that spread, we can maybe hope to constrain that spread. I'm now going to move on to talking about the different types of uncertainty in more detail. So first of all, with a focus of uncertainty from internal variability. And in particular, I firstly wanted to going back to that result I just showed you, I wanted to talk about this issue of overconfidence. So in lots of different studies, it's been found that the low frequency variability of the NEO in models is underestimated in comparison to the observed world. And you can, we found that here as well in all of the CMIP models and the MMLEA models. So just to see this, for example, if you compare, like for MPI, the yellow model, if you compare like that, the whiskers, the spread across the ensemble members is smaller than the spread that we see across the in the observations. And so what this means is that basically the uncertainty in the projections due to internal variability is too small. So we could maybe actually in the real world see an even more positive extreme future than this most extreme member here at the top. So this has large implications. And if we, so just to kind of see this concretely, we took the Mayer et al. Decomposition that I just presented, and we replaced the internal variability from the models with the observed internal variability. And what that did is that it showed that if you took the real world variability, about 50% of the uncertainty is from observations and 50% from model differences. So quite a bit more. But what I would say is that it is at least hopeful that still a large proportion of the uncertainty is from model differences. So we can still hope to constrain quite a bit of that uncertainty potentially.
Christine?
So it's not all bad news. Yeah?
So I have just a quick question, more than my lack of familiarity with the literature. So I know this. Yeah. I know this issue of the kind of overconfidence, that is the underestimate internal variability. Has anyone showed that or has anyone distinguished the or separated the role of an underestimate and SST variability to that? So were you to run kind of AMIP runs, is this an atmospheric thing or is this SSTs? Has anyone parsed that out?
I think, so I do know that there have been studies that have looked at the magnitude of the low frequency SST variability. So in terms of the Atlantic multi-decadal variability, I think that was actually Isla Simpson in her paper in 2018, and found that the models didn't underestimate that. So they're not underestimating the magnitude of the ocean variability. And I think they presented various arguments that suggested that it's the coupling between the ocean variability and the atmosphere above that is not being represented well enough in models, perhaps due to resolution issues, like it not being high resolution enough to resolve the the dynamics in that exchange. Okay. Does that make sense?
Yeah, I think, and I've seen actually Isla present that. So thanks for that reminder. Yeah, thank you.
Yeah, no problem. Okay, so moving on to, I was going to talk now about the second research question from the perspective of internal variability. So answering this question, to what extent does the NEO explain the total spread in the North Atlantic circulation projections from internal variability? And I'm going to talk about the circulation here in terms of mean sea level pressure as being representative of that circulation. So this figure here shows for each of the large ensemble models, it shows the intermember variance at each grid point in the winter mean sea level pressure anomaly for this late 21st century period with respect to the baseline period that I was using before. And what we can see is that in all of the models, there's a large spread from internal variability in high latitudes, also in continental Europe, and also in the central North Atlantic. And so to determine the extent to which this spread is due to the North Atlantic Oscillation, we made use of the historical NEO loading patterns in those models. So by that, I mean the relationship between the NEO index and this mean sea level pressure anomaly at each grid point. So to get these patterns, what we did is in each ensemble member, we take the time series of sea level pressure anomalies, regress that with the NEO index. So we've got that for each ensemble member. So a regression slope at each point, and then we average all those regression slopes across the ensemble. So this shows the ensemble mean NEO pattern. And so then, now we've got those NEO patterns, what we do is, so in each ensemble member, we take the NEO index for that ensemble member, and we multiply that by the historical NEO pattern. This gives us the spread in the NEO contribution to the projections. We can then calculate the variance across those ensemble members to give us the NEO part. And so this is the original total spread here, and then this is the spread due to the NEO. And then the residual is just the calculated from the difference between the total and the NEO part. On the lower row here, we have figures showing the proportion of variance explained by the NEO. And what we can see is that in large regions of Northern Europe, northern latitudes, and in large regions of Southern Europe and around the Mediterranean area, the NEO explains a large proportion, over 50% in some places, of the total variance. But we did notice that in the residual, there was quite a lot of residual variance in the central North Atlantic, and we thought this might be related to the East Atlantic pattern. So this is the second mode of atmospheric variability in the North Atlantic sector, and it's characterized by a monopole in sea level pressure in the central North Atlantic. So we reconducted this analysis, but also included the East Atlantic pattern using the same methods as I described for the NEO. And this figure is the same as the figure before, except for this middle row. It now includes the contribution of both the NEO and the EA pattern to the spread in the sea level pressure projections. And what we can see is that if you look at the residual, a lot of that residual variance has disappeared now. And if you look at the proportion of variance explained by both the NEO and the EA pattern, there are large, even larger regions of the North Atlantic sector explained by these modes of variability. So in short, the spread in projections from internal variability is largely explained by the dominant modes of atmospheric variability, perhaps as we would expect from previous work by Clara Dazer. But this study is useful because it builds on previous work, which has only looked at single model large ensembles, whereas this is generalizing it to multi-model large ensembles, and we see we get the same conclusion from various different models. So it's it's nice to see that result is robust.
Christine?
Mm-hmm.
Is there any reason, or are there previous studies to suggest that this East Atlantic pattern may be more coupled directly to the AMOC than the NAO per se, or is that not?
I'm not sure, I'm afraid. I haven't read into that very much, so I wouldn't want to talk about it if I don't really know.
Yep, just curious.
Yeah, sorry.
No,
Sorry. Maybe someone else here has the answer to that. Yeah, okay, so moving on. So I'm now gonna focus on the uncertainty in the forced response. So firstly, I was going to address this question of the time of emergence. So in particular, this third question of when do the forced NEO response and when do model differences in this response emerge from internal variability in the 21st century. So this figure shows projections of the NEO index for 20-year periods, consecutive 20-year periods throughout the 21st century. This is the original period that I was showing. The circles again show the ensemble mean for the large ensemble models. And then the black whiskers this time show the 95% confidence intervals. So when those intervals are no longer overlapping from zero, we know that the response, the forced response in the model has emerged from internal variability. And then similarly, if two models' confidence intervals stop overlapping, you can say they're distinguishable from one another. So if we look at this early 21st century period, 2020 to 2039, you can see that almost all of the forced responses are not different from zero statistically, and they're overlapping strongly with each other. If we then look at this later period of 2060 to 2079, you can see that most of the model forced responses have emerged from internal variability. And then if we look at this late 21st century period, 2080 to 2099, this is when we see notable structural model differences. And this is so referring back to that decomposition that I described before, this is when the model differences first become larger than the spread due to internal variability. So you can see in this earlier period, the internal variability is still slightly larger. And so the upshot of this is that the uncertainty in NAO projections, while they are potentially reducible for the late 21st century, for most of the century before that, they're not. And again, just to raise the point that this study is, because it's used a multi-model approach, this has been beneficial, because you can see if we look at individual models such as GFDL, you might conclude that the forced response emerges much earlier than the models generally suggest, and also you might conclude that the model differences also emerge earlier than if you took like two models that are much closer to each other. And so yeah, this highlights this benefit of using the Multi-Model Large Ensemble Archive in this study. So now moving on to this fourth question of the ensemble size, and specifically what is the minimum ensemble size required to separate the forced NAO response and model differences in this forced NAO response from internal variability. I'm first going to explain this from the perspective of just separating a single model's forced NAO response. So to do this, we just simply take a student t-test and rearrange it for n, the ensemble size. T here is the value of the student t distribution for a probability, a confidence interval, confidence level, sorry, of 95%. And then sigma here is the standard deviation in the means, so the 20-year means. The difference is the forced response magnitude. And so here I plotted how n varies as you varied this, the magnitude of the forced response. And we can insert lots of different estimations of the internal variability, sigma. And so the coloured lines show the estimations for the large ensembles. The grey shaded plumes show the spread across the CMIT models based on the pre-industrial control runs. And then these black lines show the estimate based on observed internal variability, low frequency internal variability. And as I alluded to before, we know that models generally underestimate the observed internal variability. So if we take this realistic estimate, that gives us a more conservative estimate of n. And so any subsequent results that I'm going to state are going to use this more conservative estimate, because it's better to be more conservative than not. And so if we take, say we take a forced NAO response of about 1 hectopascal. So this is, I've chosen this because it's in typical or in the middle of the kind of range of changes modeled by the late 21st century. So to detect a difference of 1 hectopascal, we need about 15 ensemble members. If we then said that we wanted to detect a difference in forced NAO response of 1 hectopascal between two models, we can estimate this in a similar way. So in this formula, we just replace sigma with differences in 20-year means, and the difference is just, it's the difference in forced response instead. And so for a difference of 1 hectopascal, we need about 30 members, so it's about double. So this really highlights the real need for large ensembles to detect forced NAO responses robustly from internal variability. And we see there being kind of two applications of these results. So firstly, for use in emergent constraint techniques. So typically, when we're wanting to derive an emergent constraint, we need to know we need to robustly know the forced response in a model, and we need to know that there are robust differences between those responses in order to be able to construct, a robust relationship. And so we're suggesting that studies could use this information to know if you have a large enough ensemble to be able to use emergent constraint techniques. And then secondly, for future model intercomparison experiment design, we think it would be useful for these designs to take into account the ensemble sizes that might be needed to detect some more regional changes, like changes in the NEO, because of the relevance of the impact of those changes for people on the ground. And now I've just got one final result to present to you, and this is going back to this second research question, but from the perspective of spread in the forced response. So in particular, asking to what extent does the NEO explain the total spread and the forced circulation response across the models. So this figure here shows in the top row, it shows the ensemble mean winter sea level pressure anomaly for this late 21st century period again. Again, I've decomposed this into an NEO part and a residual. To get the NEO part, you just calculate the NEO index from the ensemble mean response here, multiply that by the historical NEO pattern, and that gives us this. The residual is just the difference. And what we can see is that there's quite noticeable differences in the ensemble mean pressure anomalies. In particular, some models have a really strong dipole-like feature, so GFDL, MPI, Styro, so yeah, latitudinal dipole-like feature, while other models don't. And we can see this is largely due to spread in the NEO response. So say take GFDL, we've got a really, really large NEO response here, and the R-squared value shows the resemblance, the percentage of variance explained by the NEO of the total response, so about 80% in this case. At the same time, though, there are really large residuals in all of the models, and so there's still a large spread remaining even when we take out this NEO congruent part. And this far right column here aims to kind of summarize this. So we've got the total intermodal spread in the forced MSLP response here, and then the NEO part, so the kind of variance across these, and then the residual is just the variance across these. And so we can see, while in some regions of high latitudes and in southern Europe, the spread is well explained by the NEO, there are large regions of the North Atlantic sector that are not explained by the NEO. And so the kind of implication of this is that improved understanding of the NEO alone may not help to constrain the reducible uncertainty in North Atlantic mean sea level pressure projections. And we found this somewhat surprising given previous work by Clara Dazer and others that demonstrates the resemblance of externally forced responses to the internal modes of variability. But one thing I should note is, for the mean sea level pressure variable, if you take, say, regions of high orography, such as Greenland, there may be differences in the way that a model extrapolates the pressure anomalies down to mean sea level that may contribute to some of this large spread. Also, the temperature anomalies are included in that extrapolation, and so some of the spread may be reflecting differences in temperature rather than circulation. So these are just a couple of things that we are speculating could be, causing some of this residual spread. And because of this, we thought we might pursue looking at this question as well from the perspective of the zonal winds in the lower troposphere. The reason we didn't focus on that for the main results of the study is that there were all models available for the mean sea level pressure variable, whereas for zonal winds there's only 5 models available, and already 7 models isn't really enough to be calculating intermodal spread. But we gave it a go anyway, and this figure shows, so that far right column, it shows the same thing but for the zonal winds in the lower troposphere. So this top panel shows the intermodal spread in the ensemble mean zonal winds, and then we have an NEO part and a residual. And you can see over continental Europe, most of the total spread is explained by the NEO. There's not very much residual variance here. And so at least it looks like for the zonal winds, the total spread is more NEO congruent. So to summarize, I hope I've shown that this study has helped to improve understanding of the North Atlantic circulation projections and their uncertainty. And we've done this in various ways, so I'll just summarize them here briefly. So firstly, we find that model structural differences contribute to the majority of the spread in late 21st century winter NEO projections. And this means that most of the spread is hopefully potentially reducible. Secondly, we showed that the NEO explains a large part of the total spread in mean sea level projections from internal variability, with the EA pattern explaining a large part of the residual. So it looks like the dominant modes of variability in the North Atlantic explain the spread predominantly. In terms of spread in the forced mean sea level pressure response, it looks like the NEO contributes less to the spread. Thirdly, we show that generally the forced NEO response emerges from internal variability around about 2060 to 2079, and model differences in the forced response by around the late 21st century, so the 2080 to 2099. And what this shows is that for most of the 21st century, the uncertainty in projections is largely irreducible. And then finally, we quantify the ensemble sizes required to detect a robust NEO response and model differences in the response for a given response or difference in response magnitude. So if we take a 1 hectopascal difference, typical of the changes modeled by the end of the 21st century, so about 15 for a forced response and 30 for a difference in forced response. So we hope that this will provide some useful information for things like emergent constraint techniques and future model intercomparison experiment design. And I just wanted to finish up by talking about a few open questions and kind of ideas for future work and what we are currently doing. So first of all, there's a kind of an elephant in the room that I haven't mentioned yet. So it's this idea that asking whether the NEO projections themselves are actually underconfident. So there's been lots of studies over recent years which have shown that predictable seasonal variations in the NEO in winter are a factor of too small in models compared to observations. And then when you look at decadal predictions, this factor is a factor of 10 underestimation. Now, we don't know if this signal to noise issue affects the multi-decadal projections. It's quite hard to determine that because of the short observational record. But if it does, then clearly some of these results will be affected by that. So, for example, our key result, if models are underestimating the forced NEO response, it may be that the contribution of model structural differences is much larger. And similarly, we could that the issue of underconfidence would affect these conclusions too. This is something that would be really, really useful to look into more and understand better, because it will be important for our ability to be able to use the projections from the models, usefully. And a second thing is that, so we know that for the late 21st century, a large part, well, based on the modeled internal variability, a large part of the spread in the forced circulation responses, a large part of the spread in the models is potentially reducible. And so now what we need to do is better understand the mechanisms that cause that spread in the forced circulation response across the models. So we suggest that you could use, it'd be interesting to use the Multi-Model Large Ensemble Archive to investigate these mechanisms further. Obviously, a problem of this is that we've only got 7 models, and so trying to look at relationships across 7 models is quite difficult. So maybe the large ensembles could be used in conjunction with the CMIP models to kind of look into that more. And then secondly, we think that doing some targeted modeling experiments with different SSTs could be insightful. And so we've started doing this. So the idea is, so we take just one climate model and we take the projections of the ensemble mean winter SSTs for the future and impose them in that one model. So do like 6 different experiments with these SSTs and then see what are the differences in circulation. We have ideas to expand this, so like just extracting, say, what are the differences in the global temperature fields and imposing the differences in the global temperatures to see what effect that has. Maybe look at differences in the strength of the North Atlantic warming hole, impose the different tropical SSTs to see if that has an effect. So this is ongoing work, so yeah, hopefully we'll get some insight from that soon. But that's all from me, I think. So thank you very much for listening. If you have any questions, I'll be very happy to answer them. I'll just move back to the conclusion slides, so you can just mull over them and maybe it will prompt some thoughts. But thank you very much.
Great. Thank you, Christine. That was a really nice talk. Really nice presentation. So at this point, I'm going to go to the audience and see. I haven't noted any questions in the chat, but if somebody wants to raise their hand or ask a question, please do so. So I guess as we're waiting for more feedback, I mean, I understand you're limited to 7 models and you're so constrained with the variables that you have, but so there was the Charlton Perez, CMIP 5 question of high versus low top and models, and is there any kind of difference there? Have you, I know again, with the limits of this, is there any kind of maybe suspicion that one of the contributions to the structural uncertainty does derive from strat-trop coupling, or is it just too hard to tell? Like, do the high top models look distinct in any way?
Yeah, so I know that there was an interesting study by Thomas Hadar, I think last year, where they looked at they regressed the spread and the jet projections in the North Atlantic across all the CMIP 5 and CMIP 6 models with various different like drivers. So I think one of them was the strength of the polar vortex change, and there was like various other things like differences and tropical SST gradients, stuff like that. And I do remember that, yeah, the differences in the stratospheric circulation change did have a strong relationship with, I can't remember it specifically, but there were some large regions of the North Atlantic where the regression was really, really strong. And so I would speculate the differences, yeah, in models, whether they're high top or low top, and their ability to capture the stratospheric change. I would imagine that would have an effect, but obviously I have looked in the large ensembles at like the relationship between the NEO index change and various drivers, things like the strength of the polar vortex change and SST differences, and like there's no kind of really, really clear thing that comes out just from a kind of simple look at it. So I think it would need some more detailed look. I'm not sure how, but yeah, I hope that, I don't know if that answers the question.
No, that's great. Yeah, no, these are complicated questions, many things going on. So maybe just still more emphasis for kind of clean frameworks where we can, cleanly isolate. So yeah, great. So does anyone have a question that they would like to ask?
Hi, Clara. Can I ask a question?
Oh yeah. Hi, Ron. Great.
Hi. Yeah, this is really interesting work. Thank you. So So I guess one question is like, I mean, you've identified that there's a lot of structural uncertainty in the models. And so I guess the obvious question is, how do we reduce that? And I feel like at the very end, you talked about that a little bit in terms of trying to do perfect model experiments where you look at various, factors like SST, or tropical convection or things like that. Um, I guess the question after that is, how do we actually fix these things? Do you feel like, for example, sometimes if we have, problems with, with clouds, we might look at the microphysics or something. But here it seems like, making changes or trying to make improvements is a much more holistic process. So
Yeah.
do you have any general strategy you can offer for reduce the structural uncertainty?
No, that's a fair point. So it's just one example. So that same Udara paper, they looked at like the relationship between the jet changes, the jet shifts, and the climatological jet bias, so the bias in latitude. And so, for example, you can imagine if you constructed a relationship between the forced NEO response and like the climatological jet latitude in each of the models, and then you can identify what is the observed jet latitude, and that might help to constrain the relationship. So I guess things like that is what I have in mind. I know that then makes it sound much more simple than it probably is, but that's the kind of basic kind of understanding that I would start with.
Right. Okay. So I mean, I guess the challenge after that is trying to figure out like why some models misplace or why they put the jet in the wrong place. But
yeah.
Yeah. Well, I mean, obviously, it's a very open-ended and very difficult question. So I'm sorry to drop it on in your lap.
Oh no, it's fine. It's fine. It's the big question, isn't it? And like, yeah, it's frustrating, I'd say.
Well, thank you.
Thanks, Ron.
Any more questions? So I can't see any other questions in the chat, but Christine, I wanted to thank you again for this really great talk. You raised a lot of interesting questions. Ron has kind of nicely commented off those, and these will inevitably come up in model development discussions that we have. So
Yeah.
So thanks again. And I want to remind everyone that this has been recorded and will be posted in about 1 week. So thank you very much to Christine, and thanks to everyone else for coming today. And I hope you have a great week.
Thank you very much, Clara, for hosting. And thank you everyone for having me.
Great. Yeah, thank you.
Have a nice evening.
Thanks. Bye, everyone.
Okay, bye.